Okay, hopefully you guys got a chance to take some data from that lab. It's not particularly hard to do. Probably the hardest part was reading the scale. Um, if you thought that was difficult, you can imagine how difficult it would be to do it in real life if you actually had to find a dot and actually see it and get it to stay. It's an extremely difficult lab to do, and that's why Millikan made his grad students do it instead of him. So basically the only two pieces of data you take from the lab are the drop radius and the voltage. It did tell you that the density of the oil was 900 kilograms per cubic meter. And so once you find the volume of a drop using the radius, all you have to do is multiply it by that density to find its mass. And so if I take my first one, my first one was 395 times 10 to the negative 9 meters because it was 395 nanometers. So I'll go 4/3 times pi times 395 times 10 to the negative 9. And if I do that, I get a volume of I have to cube that. Don't want to forget. 2.58 times 10 to the negative 19 cubic meters. And you might think, well, that's a ridiculously small number. Well, it's a small, tiny oil drop. So if I take that volume and multiply it by 900, I get the mass. And the mass of the oil drop is then 2.32 times 10 to the negative 16 kilograms. So I'll put that in my table. Just one thing I want to point out on with the set of data as well. You'll notice that just because the drop radius is smaller does not actually necessarily mean that the voltage is going to be smaller, because a smaller drop could still end up with more electrons on it than the drop before it. So this is an experiment that kind of does have a number of changing variables. Luckily for us, the amount of charge on one electron is fixed. So we had the case where Fe equals Fg, like I showed you yesterday. And Fe is E times Q, and Fg is mg. And then for the electric field, if we know the distance between the plates, which we do, the distance was 3 millimeters, or 3 times 10 to the negative 3 meters. And we know the voltage, so we can write this as V times Q, times Q over D equals mg, or Q is mgd over V. So when we fill all that in for this particular oil drop, and the voltage for that first oil drop to get it suspended was 14.2 volts. So I get a Q of 4.8 times 10 to the negative 19. Okay. And then we can just set up a ratio. We know that one electron has 1.6 times 10 to the negative 19. And so we want to know how many electrons this is. That gives us 4.2. And that is
what?
Oh, 4.8, sorry. Okay, so 4.8 divided by 1.6. And it does get you very, very close to 3 electrons. So mine, it says 3.00956. Okay, so within that little margin of error, we do get a semi-precise number of whole number electrons. And you should then be able to do the same thing for the other trials. Did anybody have any questions on that lab and how it worked?
No.
Okay, so I guess I probably should have warned you about this yesterday. Oh, hang on. Okay, well, I'll leave the link up for the lab anyway. If you do or didn't get a chance to do it yesterday, it is still there. Just remind you that it's on Google Classroom here. Not in Math 10.
Physics 30 with Mr. Cooney. Who's Mr. Cooney?
The physics teacher from Valley View.
Um,
So it's here in the materials section, oil drop simulation lab, and then click on the link, and it will take you
I'm just gonna.
to the apparatus. Daniel, did you get your audio issues resolved?
Yeah, I fixed it. I just had to restart, but you're still kind of cutting in and out.
Let's see. I can maybe change my mic settings.
Millikan oil drop apparatus made in Chicago.
Is that any better? Yes, no?
Yeah, it seems better.
Okay, well, we'll see how it goes. All right, so the other thing you're going to need to do from Classroom, if you haven't done so already, is I've attached quite a while ago the blank examples for magnetism. So this, for the last bit of Unit B, this will be what we'll use. And so, I don't know, there's 24 pages apparently. If you want to print off the ones from today, it's just the first 3 or so. So we will be taking a look at magnetism and magnets. We'll just do a little bit today and a little bit tomorrow, and that will be that. And I do have some videos to show you guys today, so we will put them up eventually. Okay. So the first question is, how do magnets work, and what makes a magnet?
Wizard did it.
So obviously, if you've ever used a magnet, you've discovered that a magnet doesn't just stick to anything that is metal, and not any type of material can be a magnet. And the reason for that is there's only certain materials that we can either make into a permanent magnet or be attracted by a magnetic field and be temporarily magnetized. So things that can be acted on by a magnet or temporarily magnetized are called ferromagnetic. Now, what actually makes a ferromagnetic substance the way it is kind of a subject of rather complicated and intense debate. We do have a way in which to explain it that's kind of a simplified version, but still more or less explains pretty well why we see things behave like they do when they're a magnet. So before I draw what that is, do you guys know some examples of some ferromagnetic substances?
Neodymium.
Iron is correct. That's where the ferro comes from. Nickel, cobalt.
Neodymium.
Yeah. Neodymium and alnico.
As
These
opposed to
alloys.
oldidium.
Okay, so those are mixtures of metals that particularly good permanent magnets.
So
No.
neodymium.
Pardon?
What is like the mixture of metals that neodymium is?
I would have to look. Let's see.
Iron itself, I think.
Isn't neodymium an element?
Yeah, I
It's
thought
a-
it was.
Is it?
Yeah, it is. I got a bit here, actually.
What a time to be alive.
Number 60.
So what allows these things to become magnets or to be magnetized? Well, let's look at an unmagnetized substance first. So if we just look at regular old iron, if you take a piece of iron out of the ground, it's not going to be magnetized. And the reason for that is if this is a chunk of iron, this is iron, what it has inside it are what are called tiny little magnetic domains. And these magnetic domains are just the particles, and they're randomly oriented. So maybe we'll have one going like that and one this way. Here.
Kind of almost sounds like something someone in the 1800s would have thought of. These
Um,
little magnetic domains.
Little magnetic particles inside everything.
Of this magnetic fluid.
So if something is unmagnetized, the magnetic domains are random. And the magnetic domains serve as individually tiny little bar magnets. And just thinking about vectors, if all of those bar magnets are pointed in a random direction, what would be the overall magnetic field if it's random?
Nothing.
Yeah.
Seems you may need a new tip almost.
Oh, I'm sweating on the screen, as
Oh.
disgusting as that is. Disgusting.
Disgusting. Yeah.
So, these ferromagnetic substances are different though, because when they are influenced by a magnetic field, so that's something that's magnetized, if we apply a magnetic field, which we represent with B and a vector,
Oh, that makes total sense.
oh, come on. If we apply a magnetic field to that same piece of iron, what are we going to see happen?
The magnetic domain straighten out.
Yeah, because the substance is magnetic, those domains can be, or because it is a ferromagnetic substance, those domains can be influenced by a magnetic field. And if we have one magnet, if we just imagine a magnet, it's going to attract and influence the other magnets, and in this case, the magnetic domains inside. So let me just make sure I draw this correctly. Okay, so we'll talk about this a little bit later, but magnetic field lines always come out of north and into south. So if you don't remember this from like grade 3 or 4, talking about magnets in science class, the shaded end of a bar magnet is the north side. And so what this external magnetic field is going to do to the iron or to the ferromagnetic substance is line up all of the magnetic domains such that the magnetic field is then coming out of north and pointing to south.
Neat.
Yeah,
No.
I'm agreeing with what Bradley says. This seems kind of like a weird 1800s hypothesis.
It kind of is, but it's like an 1800s hypothesis that explains it pretty well overall. Like there's not a lot of holes you can poke in magnetic domain theory. First of all, this explains why when you cut a magnet in half, you don't end up with a north pole and a south pole. You end up with just two smaller magnets, because the magnet itself is made up of these tiny magnetic domains. And if I were, for example, to cut it right here, I would still have a piece of a magnet with a north and a south, and another piece of a magnet with a north and a south.
Oh.
So if you somehow came up with like a magnet with one pole, you would just like shatter this entire theory.
Yes.
Oh, okay.
So part of the search for like a grand unified theory of physics is finding a magnetic monopole, so a magnet that's only a north or a south, and they can't do it yet.
So what these like? Is there like actual particles in a magnet that are the magnet? Like,
Yes, like yes and no. You got to consider the magnetic domain to be kind of imaginary, but yes, the particles or the pieces of the material that give it its magnetic properties do in fact line up. And so there's like 7 things that this domain theory explains that I'm going to list, and I'll talk about how we observe each of them.
oh Lord, okie dokie.
7 commandments of magnets.
All right, the first one is probably one that you did at some point as an elementary student as a science experiment. Magnetizing a needle. So if you recall back to elementary school, how did you magnetize a needle or an iron nail?
And I just scratch them up against each other.
No.
You like take another magnet and like rub it on the needle?
Yeah, so you can magnetize a needle by moving it in one direction across a magnet.
Moving what?
The needle.
Oh. Okay.
Now, why do you think that magnetic domain theory explains this? Taylor.
I honestly don't know.
So if I were to imagine this piece of iron here, and I moved it in one direction across a magnet, what would probably happen?
Like,
Oh yeah, go ahead.
what are you moving it across?
A permanent magnet. Right, so I take like an iron nail and I drag it across a magnet. And then what happens to the nail? Well, the nail becomes a magnet temporarily, right? You can pick up like paper clips with it. So what effect probably did the magnet have on this like piece of iron that's unmagnetized or was unmagnetized?
It's giving it. It's magnetizing it.
Yep, so it's lining up
Like,
the magnetic domains. So this only works if you drag the nail in, or it only works very well if you drag the nail in one direction across the magnet. So you have to like drag it across, pick it up, and then do that over and over again. And what that does is that slowly orients all these magnetic domains in the same direction. If you just randomly rub the nail on the magnet, it won't work nearly as well. It might line up the odd few domains, but you won't get as strong of a temporary magnet by even close.
So does the permanent magnet then lose some of its magnetism because of that?
No. So let's think about this. Does that nail stay a magnet indefinitely?
No.
No. And it's actually the properties of the iron. So a softer form of iron, like what's in the nail, will have those domains line up, but then there's nothing holding them in that place. So eventually the magnetic field of the Earth and just those particles moving back to their original position, they're going to orient themselves back randomly.
Do they naturally want to be attracted to one another? Like a north attracted to a south, and they would just all line up? Why are they like random in nature?
Because it's not that there are tiny little individual magnets per se in it. It is the particles like that provide the field are either random or lined up. And so in really hard steel, if you did this with very tough steel and drug it across a magnet, you wouldn't generate a temporary magnet, because in that hard steel, the particles or the domains within the hard steel can't actually orient themselves. They can't move.
Okay.
And so for other materials, if they have magnetic domains at all, things that can't be magnetized, so something like aluminum, the magnetic domains aren't movable in such a way that they can be influenced by a magnetic field. Okay, the second one we already talked about, a bar magnet cut in two. Produces two smaller magnets. And if we just draw a really quick picture with some magnetic domains. If we cut it in two, there's still in each piece magnetic domains that are oriented in that same direction. And so you can think of them almost as infinitely small. So you could cut a magnet in half. If it's a magnetic material, you can cut it in half again, and you're still going to end up with a north side and a south side. So if this was north and this was south, if you cut it in half, it will still have a north side and a south side. All right, I'd like you guys to think about this one. So heating, hammering, and dropping a magnet.
Sounds like a Friday night for me.
Can cause it to demagnetize.
Sounds like someone has a snap of the chat.
That was me.
Hmm.
That's right. I know what Snapchat is.
How do you do, fellow kids?
Funny explaining magnets with smaller magnets.
Okay, so Shaden.
What?
Why do you think that heating, hammering, or dropping a magnet might cause it to demagnetize? What effect are we possibly having?
I don't know. All at once, you mean? Or one or the other?
Like any of the three. Like any of those three things, if I do it to a magnet, it can cause it to demagnetize.
Don't know.
And
You're introducing kinetic energy.
true. What might I be disrupting?
You're
With
disrupting like the bar magnets that are in there. The field. That's what it is. No, what's domain? Domain.
So what we're actually doing, if we heat it up, if we hammer it, if we drop it, we're potentially disrupting the orientation of those magnetic domains.
That looks like an R. Thomas would draw.
Shut up. That one wasn't much better.
Well, you tried. It's the thought that counts.
There's like places on the screen that don't want to write currently, and I don't know why.
Cest bizarre.
Okay, so just like we can magnetize something, we can also introduce this type of stress that knocks the magnetic domains out of place. And so magnets, like bar magnets, cheap bar magnets that are stored properly, they have these little magnetic keepers on them, and you have to store them in such a way that a north and a south are next to one another, and that's just so that the magnetic domains aren't being interfered with in those cheap bar magnets. Otherwise, every couple of years, you have to go and remagnetize them.
Would small electric motors, would they face that same problem?
Not quite as much because they use much stronger, better magnets. But the heating part, possibly. The just losing magnetism over time, not so much. Now, this one's a pretty neat fact. Ships' hulls and other iron products, other large iron products,
You're a popular guy today.
that's a news story.
Oh. What 5 facts does BuzzFeed want you to know about now?
I don't know.
Bet you won't believe number 7.
Bradley, you said 5.
That's the joke.
Okay.
So you can actually tell or figure out where a ship was built on Earth based on its magnetic signature. So the ship's hull, made of iron, you can identify where it was made based on the orientation of its magnetism. Why might that be?
Because there's different.
The Earth's own magnetic field has an influence over the metal.
Yeah, so when the iron is being forged, it's obviously hot, and it's then much more susceptible to changes in its magnetic domain. And so as the iron cools, the Earth's magnetic field is going to have an influence on it, and the direction of that magnetic field is going to be different depending on where you are on the Earth. So if you're close to the North Pole, for example, it's going to be pointed in a certain direction. If you're closer to the equator, it might be pointed in a different direction relative to where you are. But then as that iron cools, it locks those magnetic domains into place, and then it kind of has this semi-permanent orientation of those magnetic domains based on where it was made.
So the USA could make nuclear warheads in a magnetic building and then say it was from Iran.
Thinking outside the box there, Ethan. I like it.
So the hot iron has magnetic domains that are influenced by the Earth's magnetic field. I always forget to capitalize Earth. Okay, now I said there were 7. There are various things that are just related to these facts. So, for example, if you mine minerals, you can observe the same type of phenomenon, that they have magnetic domains that are oriented with the Earth's magnetic field. If you take a very, very strong magnet, you can reverse the polarity of a weaker magnet simply by the strong magnetic field completely reorienting the domains. And so the idea in general is that we've got these magnetic domains that are inside these ferromagnetic materials. We can influence them with the magnetic field. And if we lock them in place in a specific orientation like this, we can influence other objects.
What makes some magnets stronger than the other?
Either the amount of magnetic domains, more or less, or how well they can be locked into place. So like I drew this for iron, but that doesn't mean that every single magnetic domain in iron is in that orientation. There could, and there likely is, still a bunch of ones that are random. But in something like neodymium, it has a lot of magnetic domains that all can be locked in the same direction for a very long time. And so then the magnetic pull is quite strong.
Okay.
Any other questions about this so far? Otherwise, we're going to go on to magnetic fields and I'll show you some videos.
Can Zoom play audio over like screen recording or whatever? Screen sharing?
I can, I just have it turned off.
Oh.
Because then there would be 2 microphones picking me up and one is plenty.
Another latte?
Yes, it was actually.
Oh. Did you just go to Crockett House and get it, or did you make
No,
it?
I have an espresso machine at home.
Oh, fancy.
Okay, magnetic fields.
As opposed to a grass field, or a wheat field, or an electric field.
Okay, so I'm now going to try and share my screen eventually. So with magnetic fields, this is definitely one of the things that would have been really good to do in class. So you can check out the bar magnets, and you can spread iron, which we know is a ferromagnetic substance. It can be influenced by magnetic fields. If you shake iron filings, so with small, tiny little pieces of iron, you can actually visualize, you can actually see for yourself the way in which the magnet is influencing the iron. And so just like for a gravitational field or an electric field, how we describe a field is a zone of influence. I.e. exerting a force. And so with a magnetic field, it's a little bit different than a gravitational field or an electric field, just because magnetic objects are small, but they have physical space. And you can see, well, I'll show you very shortly, that the orientation of the field lines is a little bit different than what we've come to expect from gravity, from a single particle emitting a field or drawing particles towards it. So, can I share my screen? Let's see. Can you guys see that?
See.
Okay. So what they've got here is just kind of a plastic surface, and they've got some iron filings with that bar magnet. And what they're going to do is, I don't know if the audio will play or not, they're going to sprinkle those iron filings around the bar magnet, and you will see how the iron filings are influenced by the magnet.
Now, sprinkle some iron filings on the paper.
It does
Stack the
play
paper
audio.
slightly such that iron filings arrange themselves. Observe the pattern made by the iron filings.
Observe.
If you look at the pattern, you will see that the iron filings have arranged themselves in curved lines that originate from one end of the magnet and terminate at the other.
So, can you see my pointer too?
Yes.
Okay. So I don't know which end is north and which one is south, but if we follow the magnetic field lines, what they're doing is they're exiting one end of the magnet and then curving around and actually entering in the other side of the magnet. So we have these curved field lines, and they are either going into one side or coming out of one side, bending around, and then going back into the other. And then within the magnet itself, those field lines are continuous. So we're kind of used to, with gravity or with an electric charge, either the field lines originating from an object, whether it's a mass or a charge, or going towards an object. Whereas in this one, it's kind of a continuous flow of those field lines. But the same thing is true that the more field lines you see, the stronger the magnetic field is. And the closer they are together, the stronger the field is. So play the rest.
Also observe that the concentration of the lines is more at the poles of the magnet. Most of the lines run from one pole to the other. If we draw a diagram of this on a paper, it will look like this. The long curved lines shown along a magnet are called the magnetic lines of force. They run from the North Pole to the South Pole. The space in which the lines of force are spread around a magnet is called the magnetic field. The characteristics of the lines of force are they attempt to form closed loops from pole to pole. They never intersect. They all have the same strength. The number of lines of forces per unit area determines the...
Okay, and we've already talked about that kind of stuff before. Okay, so that was the first video. Stop here.
So those magnetic lines, they can't be intersected, but could they be interrupted?
How do you mean?
Like, instead of going straight from north to south, could another magnet, influence them?
Yes. So if we just have one magnet, if we have a north and a south side, so those lines do come out of north and bend around to south. Okay. And that's a general rule you're going to have to know, just like the direction of an electric field is the direction that a positive charge would move. You need to know that magnetic field lines are oriented in such a way that they're going from north always to south. So from north, and they're pointed towards a south pole. Now, if they're always pointed towards the south pole, that means that if we have two magnets lined up in this direction, then particularly between those magnets, some of the field lines are going to look like this. They're actually going to be quite straight because they're going straight from north to south. But there will be the occasional field line that still wraps around like this.
So would they bend? Like, would the North Pole from one magnet bend towards the South Pole to the other?
The north from one, and
Like,
would it, instead of drawing it the same as I did the first time, kind of look like this? Is what you're
no.
No.
Hold on here. I'll draw it. Just 2 seconds.
Can you?
Yes, I can. Just a second. I can move my webcam and turn it on. Then y'all don't have to see me. How do I turn it on? There we are. Start video. Like that. Nope,
Hang on.
like that.
Hang on. I'm trying to find where your video is.
Right.
Oh, there we go. You gotta get closer. Oh, I see.
Yeah.
But you're drawing that one from south to north.
Or I suppose the other way, from north to south of the
Oh, so
different magnets.
Would I see this kind of behavior on the outside?
Yeah.
Yeah, a little bit. It's the same kind of thing as with parallel plates. So when you're kind of straight between the magnets, you see mostly straight field lines. And then as you deviate outside that, you're going to see less straight field lines.
Cool.
Yeah. So maybe when I go to the school tonight, I'll stop in and dig out some of these bar magnets and some iron filings, and I'll try to we can set up multiple magnets and take a look at this. It is a little bit messy, but so is the rest of my house, so why not? Okay, so you need to remember magnetic field lines. Always point from north to south.
So if we were to do a magnetic field line diagram of sorts, would it be similar to when we did the diagrams of the positive and negative charges?
In the sense that the closer the lines are, the stronger the field, yes. In the sense of like from the direction you can figure stuff out about the magnets, yes. But you'll notice that for this bar magnet that I've drawn, like an electric charge doesn't bend its field lines back in towards itself. And then within the magnet, which is not generally a zone we're concerned with, those lines are continuous. So within the magnet, things are kind of backwards in the sense that we're now pointing from south to north, but those are just the field lines continuing through the magnet. They exit from the north pole of a magnet and enter back in the south pole. So with an electric charge, we either see one of two things. For a positive charge, the test charge would move outwards. And for a negative charge, it would move inwards, but there's no like internal wrapping around of those within just one single charge, right? Okay, that doesn't need to be full screen.
So can you have like a magnetic particle that isn't magnetic itself, but is attracted to or repelled from magnets?
No.
No.
Because if it's influenced by a magnetic field, its domains can be oriented. But if it was itself magnetic, it would have its domains already oriented and then cause that type of influence.
Okay. And wouldn't everything in like the universe or whatever have some magnetic domain in it? Or is it something that is very specific to just those specific metals?
So this is the point at which it falls apart. It's because a magnetic domain is more or less an imaginary thing. It's hard to say.
Okay.
We know that some things can and can't be influenced by magnetic fields. What are the exact properties that cause that? Well, I don't personally know. They probably know a little bit more about that, but it falls way outside of magnetic domain theory.
Okay.
Okay, so this example is not in your handouts. This is just a random question. I would like you to draw the magnetic field of the Earth.
How do I do that if it's flat?
That's a great question.
So this is the North Pole up here. This is Antarctica down here.
You should be an artist.
I don't even know what I'm drawing. Here's Mexico. Oh, it looks something like this.
Oh, it kind of looks more like South America. Oh no, I guess that's North America. I can see it. You just need to put an asterisk and put this drawing is not to scale.
No maps are to scale. Did you I've talked about that before, right?
Which? Sorry.
Like to turn a flat mapping into a globe, or sorry, to turn a globe into a map, you have to, by nature, change some of the scaling.
Yeah.
And so
This
there's
is scale.
there's people who complain that the version of a map that we see, it makes like North America and Europe look larger than they are compared to Africa, and they say that that's like I don't know, an example of white racism. It's actually because that's the best scaling of the map that makes the shipping routes straight. So
Yeah.
like your ability to navigate requires that scaling. If you do another scaling, like the shipping routes become wonky, but then the continents are more to size.
Yeah.
But anyways,
That's what white people say to explain it.
damn white people in their shuffles cards. Lord. Georgia.
Damn white people and their shipping routes.
They're spicy. Okay. Let's see. How about Avera?
Yeah.
Which way do you think the lines point for the magnetic field of the Earth, and how might you know?
From the north to the south, like up and around.
Okay, so the suggestion, don't write this yet because we don't know if we're right or wrong, and it's like this. So if that's the case, it would be exiting from north and pointing to south. Which way does a compass point?
North.
The needle on a compass points north.
Oh my god, no.
So which pole magnetically is up top?
South.
If the north pole of a needle is pointing what we consider to be geographic north, it must actually be pointing towards a south pole because north and south are attracted. So the north pole of Earth geographically is actually a south magnetic pole.
That is dumb.
The magnet that is the Earth looks something like this. And so the field lines actually wrap in the opposite direction. They come from the South Pole and wrap around to our geographic North Pole. And then go straight through.
Oh.
So, and the straight through is inside the Earth. So if we were somewhere outside the Earth, like here, and we had our compass is going to follow the orientation of those magnetic field lines. So the compass is going to orient itself. Now, of course, we're really far out here in this drawing. If I put the compass in here, the compass is going to orient itself in this direction. Okay, the same way as the magnetic field lines for that reason. So a compass points in the same direction that a magnetic field line points.
So why do people still call the North Pole the magnetic North Pole?
Well,
Even on this globe, it says magnetic North Pole. at the
Really?
north.
Okay, so that means exactly where the quote unquote North Pole is in relation to the magnet. So what we consider the geographic North Pole, i.e. the northernmost point, is different from where the magnetism would point north.
So why'd they do that?
Well, there's a couple of reasons. The first of which is that this isn't fixed. Every 50,000 years or so, maybe it's a little longer, 50 to 100,000 years, there's actually a reversal of the magnetic field generated by the Earth. And so eventually, all compasses will point south. And, pardon?
Why?
Well, what do you think is generating the magnetic field of the Earth?
Isn't it like the magma below us?
Yeah, it's the molten core that's rotating and it's very hot, and those magnetic domains inside that core more or less are generating the magnetic field and influencing all of the iron that makes up the Earth's crust. And more or less, we get some sort of spontaneous flipping of that polarity because of the intense heat and pressure. And nobody has been alive for a magnetic pole reversal, or none of us have been. So we don't know entirely what effect it has. It's actually kind of theorized that that is part of what's caused some of the mass extinctions in the past, because we know that birds migrate using some sort of sense of the magnetic fields, and if that all of a sudden flips, well, they're going to be flying north instead of south.
Could you imagine if we could do that too and just woke up one morning feeling violently ill and every person on Earth all of a sudden had like magnetism disease or something?
Why we have the lab.
Wouldn't that happen every time you turned around?
Crap, you've poked a hole in my theory.
I don't know. So just a couple points from this. The magnetic North Pole of Earth is in Antarctica. That's the best way to describe it in terms of saying that it's at the South Pole. The magnetic North Pole of Earth is way down in Antarctica.
So then, okay, so if I go on my phone right now and I go into settings, like compass settings, it says use true north. What's the difference between true north and, I don't know, false north?
So true north is, I'm pretty sure true north means geographic north, and magnetic north, and just north means magnetic north, or maybe it's the other way around. True north might be exactly where a compass points. And so this is, again, one of those things. First of all, you know that Earth rotates on an axis, right? So that was the other point that I was going to make. So Earth is rotating at this 23.5 degrees off center. That is more or less where a compass will point. Okay. Whereas our true north is based on a map where we want the top of the world, as it were.
Right.
And so those are the two differences.
So if one of these magnetic flips ever actually happened, wouldn't that influence a lot of technology and satellites?
Potentially, yes.
So everyone's just gonna die when that happens.
I guess we'll have to wait and see.
Nice.
Okay, so we'll leave it there for today with the new stuff. So there's not really a whole lot for you guys to do after class today. Just this little bit of discussion on magnets. Hopefully I'll have a few more demonstrations tomorrow. I do have a couple other videos to show you when we get into hand rules and things like that. So what things other than permanent magnets generate magnetic fields? It's electrons, by the way.
Wow.